Dear students, today I will demonstrate you an experiment on lasers. You have already studied the theory of lasers, but before that I will explain you different types of light sources and also the big electromagnetic spectrum. So if you see this chart, these are the units we are using for the wavelengths, and the figure shows a big electromagnetic spectrum starts from here. If you look at is 30 kilohertz. Below that also we have, and then this part of the electromagnetic spectrum are under long waves, and that means the wavelength is from 10 to the power 3 to 10 to the power 4 meters. If you go here, we have medium waves, and then we have short waves, ultra high frequency waves, which from frequency of 300 megahertz, and then we have microwaves, radar waves, and ultra high frequency waves, which are used for various applications like microwaves and radar applications, etc. If you go here, we have infrared region of the electromagnetic spectrum, and if you see, this is a small part which is a visible spectrum, and if you look at from here to whole of this up to this, which is a big electromagnetic spectrum covering whole range of wavelengths, but our eye is capable of recognizing only a small part of this big electromagnetic spectrum. And this electrospectrum we call it as a visible light, where if you see, the visible light starts at 400 nanometers to 7500 nanometers, or else you can see that it is from the red light to blue light. If you come here, the small part is now extended and blown up to see various colors in it. If you see, this is a light given by the starting from 7500 angstroms to 4000 angstrom units. This is a Whipple spectrum. If you look at this and see, here we have red color, and red will have now different shades, and we have orange, yellow, light yellow, then light green, blue, and you can see violet colors. And in this, if you see this, the wavelengths, red is highest, 7500 angstrom units, and the least is blue, that is 4000 angstrom units, or violet. If you see, this is violet, and green is 5085 angstrom units. But you studied about sodium vapor lamp, which gives you two lines called D1, D2 lines, and these D1, D2 lines of sodium are here 5896 to 5876 angstrom units. And these are the different colors given by different atoms: hydrogen atom, sodium yellow, cadmium green, lithium blue, potassium violet. These are the different Whipple colors, which is a constituent colors of white light. White light by itself has no wavelength. White light is a combination color or combination of colors, and you have already studied that when white light passes through a prism or a grating, it splits into constituent colors, and thereby if you look at this whole electromagnetic spectrum, a small part is visible. And before that we have infrared, and after that we have ultraviolet, and then we have here, if you see, the changes: soft and X-rays and hard X-rays, gamma rays, etc., and then cosmic rays. And the frequency is up to 3 into 10 to the power 16 megahertz, and also more than this. Therefore, an electromagnetic spectrum consists of long waves, medium waves, short radio waves, then we have microwaves, infrared, visible, ultraviolet, X-rays, gamma rays, and if you have cosmic rays. But now we will see the different light sources, which are some of them are monochromatic, some of them are polychromatic, and we see the laser light also. Students, now the light sources are generally classified into polychromatic light sources or white light sources, or the monochromatic light sources. A composite light source or a white light source gives you several wavelengths in it. That's why we call it as a composite light source. A white light source is a composite light source. And for example, a candle which is burning gives you a white light which consists of many wavelengths in it. So this is a composite light source or a polychromatic light source. Poly means many, chromatic means colors. It contains many colors. And the light coming from sun is also polychromatic. It's also white light source. Sun is also white light source. And if you look at the tube light at the top, this is also a white light source which gives you many colors out of it. But in some experiments, especially in spectroscopy, we want single wavelength sources which are called as monochromatic light sources. Mono means single, chroma means color. So single color or single wavelength will be present in the emitted light by a source. But a candle is not a monochromatic light source, it is a polychromatic light source. Now we will see the next source in our lab. This is a candle. A burning candle gives you a white light, and the sun also gives white light. A red hot iron also gives white light. Now we will see another lamp in our lab which also gives you many colors or many wavelengths. Students, now see this. This is called mercury vapor lamp, and this mercury vapor lamp gives you white light which is consisting of again with GR colors. The colors that the mercury vapor lamp has can be seen by using a prism or by using a grating through the help of a spectrometer. But you see, we have seen this mercury vapor lamp with slits, because it gives you an intense light which spreads in the area or in the space. That's why we want a narrow beam of light, hence we have slits here. Through this opening only the light which is coming will be used, and further we use some more slits to make the beam as narrow as possible. But if you see it, if I just open this case, you can see a bright mercury vapor lamp, which we cannot of course bear with our normal eyes, because the intensity of this mercury vapor lamp is very high, and therefore we are keeping this slit box where we will get narrow beam of it. And this is an example of white light source which is a polychromatic light source. And this polychromatic light source is used for various applications, at least to find the different wavelengths that are present in the mercury vapor lamp by using a spectrometer and with the help of a diffraction grating. Dear students, again I am showing you another light source in the lab which is called as sodium vapor lamp. Sodium vapor lamp gives you a yellow color. And by our previous knowledge, a sodium vapor lamp gives you two lights called D1 and D2 lights. That means it is not truly monochromatic, but it contains two closely spaced wavelengths, maybe of 5893 angstroms and 5896 angstrom units. These two. Therefore, this sodium vapor lamp, for simple purposes you can take it as a monochromatic source, but it is not truly monochromatic, but it is containing two different wavelengths. And also you see, this is a very intense light. That's why again we have openings and slits. So you can do an experiment from the light coming here or coming here, are coming here, and you can find the wavelength of sodium vapor lamp either by using a diffraction grating, or you can do Newton rings experiment, and thereby the wavelength of the light source can be found. And this is not a polychromatic light source, it is a monochromatic light source. Roughly we consider it in lab purposes, but still it has a spectrum, and thereby it contains more than one wavelength. Hence, for normal purposes, it can be taken and treated as a monochromatic light source, but it is not truly monochromatic. Now students, we have seen different light sources. These different light sources are like a candle, incandescent lamp, sunlight, mercury vapor lamp, or a sodium vapor lamp. All these basically works on the principle of as we have studied as spontaneous emission. For monochromatic light sources, we require for lasers stimulated emission, and you studied already in our laser chapter about induced absorption, spontaneous emission, and stimulated emission. Now, to know about the laser, I would like to explain briefly the stimulated emission. So look at this picture. If you see this, we have a ground state, and if you give some energy, atoms will go from ground state to higher energy state, and this state is called population inversion state. Population inversion state is the state at which you have more number of atoms in the higher energy level than the lower energy level. And we have a metastable state. Metastable state is a state whose lifetime is more than normal state. Therefore, metastable state is a long-lived state. For lasing action, we require a metastable state. Therefore, to get a laser light which is a chromatic light, we use first population inversion, metastable state requirement, then we supply a matching photon, and that matching photon acts as an oscillator, and thereby the atoms will come down from metastable state to ground state, giving rise to the photons out of it. And if you are using an external photon to initiate downward transitions and thereby a photon emission, we call it as stimulated emission. So under stimulated emission, we supply one matching photon whose energy is exactly equal to between the two energy, difference between the two energy levels. Then this photon goes as usual, and one more photon will be released when this atom is coming down to lower energy state from higher energy state. Therefore, we have two photons. Hence, stimulated emission will give you two photons. That means the photons are multiplied or amplified. That's why the full form of laser is light amplification by stimulated emission of radiation. So, laser is also light, but it is amplified form by the process of stimulated emission, and it is a radiation. Hence, it is a part of electromagnetic spectrum. Hence, lasers may be there in green color or red color or any other color also, but they are highly monochromatic. And see this how the laser works in. We have the photons moving between two states or two mirrors and shuffling back and between the two mirrors, which we call it as resonating cavity. So resonating cavity helps us to pile up the photons, and thereby the amplification takes place. And this is the ruby laser, and this is helium neon laser block diagram, and these are the energy level diagrams. Therefore, we have to now know that when I took the mercury vapor lamp, if I open it, the light is spreading in the space around it. But if I take a tube light, it is also spreading. A candle is also spreading light, so they are highly dispersed. But we want a narrow beam, concentrated beam of light for many experiments. So what we require, or what are the requirements are, we require a monochromatic, high intensity, highly directional light sources, and that light source which meets the requirements of high directionality, high monochromaticity, high intensity is laser. Now I will show you a laser source here, and we will do an experiment to find out the wavelength of laser lamp. Now if you see this, this is one laser light source we have in our lab. This is called helium neon laser, and we have another laser source also, and this laser source we call it as semiconductor diode laser. This is semiconductor diode laser. This is a helium neon laser, and this laser gives you a power output of less than half a milliwatt, but this gives you 2 milliwatts maximum. Therefore it is high intense, but light is monochromatic for both of them because both of them uses the principle of stimulated emission, and they give you the monochromatic light and high intense beam, and they won't spread like the lamps which you have seen previously. If I just switch on the power, if you just look at the power, and if I just switch on the laser, see laser light, if I get it, see on this, so you can see that it is a spot, a single spot. It is not spreading in its way, it is not at all spreading, it's a single spot is there. Therefore highly directional narrow beam, and we get a fine spot of it. Therefore it will not disperse. The angular dispersion is very small for a laser light. Similarly, if I look at this is the semiconductor laser. This is the semiconductor laser which is giving you a light source or something like this, a part of it. So this is, see, if I keep it here, this laser source, but you see, you cannot see and should not see laser light directly with your eye, directly like this, because laser lights have a safety requirement. If you see for longer time, or if you see fraction of seconds of a high energy laser light, your eyes will be damaged permanently. Therefore we see only the images catched on a screen, and we look at those images or the spots that are there on the one. See, if you see it, you can see a spot. If I increase the distance also from this laser, the spot will not change. That means the angular spread is very small. But if you take ordinary lamp, it spreads. And now I will switch on this. Okay, see this is the helium neon laser, and if you see that helium neon laser spot on the screen, it is high intense. It's highly intense. When I keep this just below this is whatever I am moving is from semiconductor diode laser. This is not that much of intensity, and this is highly intense. But you can do an experiment in a similar manner, whether you can use a semiconductor laser or you can use a helium neon laser to find out the wavelength by using a diffraction grating. You already studied that diffraction is nothing but bending of light at small apertures or small openings, or we say sharp objects. And if you have too many closely spaced slits drawn on a glass plate, we call it as a diffraction grating. I will show you diffraction grating. So the aim of the experiment is to find out wavelength of a laser source using diffraction grating. This is diffraction grating, which looks like a glass plate. It is not a plain glass plate, but however the diffraction grating is made by drawing very closely spaced lines on a glass plate with the help of a diamond pointer. That means if you see that, I will take here a glass plate like this. You know, diamond cutter are used to cut the glasses, which are when you fix them to windows, you use a glass cutter with a diamond pointer which cuts the glass very neatly. So they will draw lines which are very closely spaced lines, so that because to get the diffraction, the requirement is that we defined the diffraction as bending of light. Where the light bends only when it encounters small objects, small apertures, sharp edges and very fine openings. And these dimensions of the opening should be comparable with the wavelength of the incident light. If the dimensions, openings and closings, if they are comparable with the lambda wavelength of the incident light, then only light bends. Actually, light bends in three different cases. One, the light bends when it is moving from one medium to other medium, which we call it as refraction. Light also bends when it encounters small openings, small edges, apertures, whose dimensions are comparable with the wavelength of the incident light, that we call it as diffraction. Light also bends when it encounters huge objects of astronomical sizes. So these are the three different cases where the light undergoes the bending. Here the bending is from a small aperture. Therefore, this glass one which I am showing is called diffraction grating, will have a very small openings and closings. But how many will be there? We should know. Generally, the manufacturer will provide you the number of openings and closings. So openings and closings are something like this. If you see this figure, okay, this is an opening from which light can come. From this is a closing through which light cannot come. Therefore, we have alternate openings and closings for the light. And the arrangement of large number of parallel openings and closings is generally called as a grating. So this is a grating. This is the arrangement of large number of parallel openings and closings. How many are there? That is important, because these should be very small and fine to get diffraction, so that the distance between them is comparable with the wavelength of the incident light to observe the diffraction pattern. Hence, this will have, if you see here, okay, the manufacturer himself will give you here, if you see closely, okay, 2000 LPI. That means there are 2000 lines per inch. So therefore, if I call this as number of slits, which we call it as N, capital N. Capital N is number of slits. In this case of this grating, if you see, there are 2000 lines per inch. Lines per inch. We have different gratings in our lab. We have 15,000 lines per inch grating. We have 500 lines per inch gratings. We have 2,500 lines per inch also. Now I have taken 2000 lines per inch. But generally we will do calculations in CGS system in centimeters. Therefore, I convert 2000 lines per inch into centimeters by dividing this into 2.54, and this gives you in centimeters. Therefore, you note down this value, where to find lambda, the wavelength of the light, we use the formula, it is sin theta by capital N into small n in centimeters. Later you can convert into Armstrong units. But if you see, theta is called angle of diffraction. Angle of diffraction. And diffraction gives you alternate bright and dark spots, and those are called orders. So this is the order of the bright fringe. Small n is order of diffraction. Order of diffraction we call it as. We will see how to measure and how to count these orders while doing the experiment. Capital N is nothing but number of lines per inch, number of lines per centimeter. They have given in inches, I have converted this into centimeters. Therefore, you should make a note of this, because while doing the experiment, we note down the value of capital N from this value, small n from the experiment we will get, and theta is the angle of diffraction which we have to measure from the suppose say experiment. How do I measure? Suppose say I have here a light source, and suppose this is the laser light coming from here. This is the laser light, and this laser light will fall on a screen something like this. This is the screen, this is the laser light. Straight away it is coming and falling it. Now I put a diffraction grating in here, and diffraction grating makes the light to diffract, means that it will bend and goes and hits on either side of the central. This is the central beam comes in. This is called 0th order. That means n is equal to 0, which is the most brightest spot. This is the angle theta, angle of diffraction. This is on same angle theta, and this we call it as first order. N is equal to 1. We call it as first order. So we have first order on either side of the 0th order. This is also n is equal to first order, and there may be another bending something like this by another theta, and this is another theta. If I take it, we will get next theta. Therefore, we can see this is n is equal to 2, which is second order. This is second order. So if I just draw this figure something like this, this is the light coming and this is the screen. Okay, we have a screen, light is going or bending it because of this one, and this is theta. And this is the distance between the grating, from the grating to the screen. This is the grating and this is the screen. So if I take this distance as d, and this is also theta, this is n equal to 1, this is n equal to 1. So I measure the distance with the help of a scale from first order on either side of the 0 order, and this distance I call it as x, and therefore this is x, this is x. So we know that this is now d and this is x, this is x, this is d. So from our mathematics we know that tan theta is x by d. So you have to measure x from the experiment, and we fix the distance of the grating with respect to the screen, and that we call it as d. So x we will measure with the help of a scale, d also will measure with the help of a scale, and I find out theta value. If I know tan theta value, you can find sin theta value, or you can find theta value and you can find sin theta value. So if you know sin theta value, substitute the sin theta value here, and you know already n is the number of slits or openings, which is now fixed as 2000 by 2.54 centimeters. N order changes with respect to our experiment. We can take n equal to 1, 2, 3, 4, 5, 6, so on. So thereby we have to note down the readings. Now I'll show you the actual experiment. Sources. Now look at the sources. This is helium neon laser, very intense. This is semiconductor laser. This is ordinary bulb. This ordinary bulb gives you light spreading and covering the whole area. So a lot of the light is dispersing, but this beam is going straight away and giving you a single spot. And now to do this experiment, what I do is I am just using here this laser light source, and I keep the stand to hold the grating at some distance. This is the source. So I am switching off all other sources, but you can also see about these filters. These are called optical filters. If this is the white light it is giving, from this white light if I want only orange light, I use this filter, and okay, so thereby what I'll get it is orange light only coming out of it. This is called interference filter. It uses the phenomena of interference and cuts off all other lights coming from the source except orange light that will come out. If I want only green light from this, I use a green filter. These are called filters to get individual wavelengths from the composite source. But if I take this is a laser source. It gives pure red color only, and there is no need of using any filters like this. And therefore, I am switching off this light, which I don't want this laser also, and I am taking it. Now, to do the experiment, keep the laser source and the grating stand at the same height, and this is the grating. Now you see, this opening is very large. Therefore, the opening is very large, which is not comparable with the wavelength of the light source. Therefore, no diffraction occurs. Exactly, the light goes, and you see, you will get only one spot here, just a spot here and there. But the diffraction light bends and goes into geometrical shadow region. This is the geometrical shadow region. Here I don't get any light, because light generally we think that it moves in a rectilinear direction or rectilinear propagation of light, means that it goes in a straight line. But we'll see how light bends when a grating is placed in the path of a laser light. This is called 0th order, which is highest intensity, also called as undeviated beam, and N order of the diffraction is 0 because it is not deviated from its straight line path. This is the one. Now I see this is the grating. If I keep the grating, so this is the grating I am keeping here. When I keep the grating in the stand, you can see that the light will bend and will go into the geometrical shadow region. That means previously we have only one spot corresponding to straight line motion. But if I see the grating, the bending occurs, and this bending gives you a lot of orders. So therefore, if you see this, it is the display. Can you see? Are you able to see the same color? But we have, this is the 0th order, first order. These are called corresponding orders. And this is also corresponding second order, third order, fourth order, fifth order. And either side you can see too many orders. If you want to make it straight, you can adjust the height and also the angle of the stand. We will get so many orders. This is called 0th order. This is first order, second order. So we will measure the distances from this, and we will enter the readings in the tabular form. So we have all this, but if you switch off the background light, it will be very dark. So I will switch off the background lights, and I will show you how to measure the readings, how to measure these measurements, and how to note them in a tabular form. Yeah, now look at this display. How many orders I am getting? This is 0th order, first order, second order, third order. That means small n is equal to 3, small n is equal to 4, 5, 6, 7, 8, 9, 10, 11, 12, and many are there. But you should observe that center is very bright. As I am increasing the orders, the intensity is decreasing. This is the main difference between interference and diffraction. In interference, all fringes are equally bright and equally dark. But in diffraction, the fringes intensity decreases with increasing order. We have maximum, minimum, maximum, minimum, maximum, minimum. This is 0th maximum, first order maximum, and in between we have a minimum. These are minimum intensity spots, and these are maximum intensity spots. So as the order of the diffraction is increasing, the intensity of the light decreases and finally diminishes. So I will take only readings for first 6 orders, that is small n equal to 1 to 6, and capital N is already fixed, that we have taken capital N is equal to number of slits per centimeter as 2000 by 2.54. That number you have to calculate and use it as a capital N. Now the formula which I am using is lambda is equal to That means the wavelength of the laser light is equal to sine theta by capital N into small n. Sine theta I have to measure from the experiment, and n you know small n from these orders. Now to do that experiment, I am now just showing you the tabular form. So look at the tabular form which I have given. The tabular form is serial number, distance between corresponding orders or corresponding maxima, means that distance between n equal to 1 to n equal to 1 on either side of the 0th order, that is 2x. I call this as 2x. So I am now drawing the tabular form, serial number, and it is distance between this. But as I explained earlier, this is the light coming, this is the grating, this is the screen, this is theta. So if I know d and x, I can calculate theta. So I have to now measure x. This is 2x actually, this is x, this is 2x. I measure 2x, that's what we have written distance between the corresponding order is 2x. Then the next column is x, make it half, just make it half. Then I'll measure the distance between the grating and the screen, and then I find out tan theta value. Tan theta is equal to x by d, from which I can find theta value, okay, and then I'll find sin theta, and then I find lambda for each and every reading, every order. So I have here orders. I will also serial number I write here, and I'll put here order. Order is n, small n. Capital you know it. I'll go for first order, second order, third order, fourth order, fifth order, and sixth order. I'll take like this. Okay. And for every order I have to find lambda. But see, orders are changing, but lambda will not change, because lambda is the wavelength of the source. And it is not the wavelength given by the grating. Grating is not a source, it is a device. Therefore, whether order is 1, 2, 3 or 5 or 100 you are taking, lambda must be the same. That means the last column should remain constant. After finding the values, you have to take average value of lambda. Here in this experiment, the laser is red. So, red color should have a value between 7500 to 6000, okay, maybe 500. For this, you should have a value in between, and you calculate and tell me what is the value of lambda in our experiment. I will show you how to take the readings, but you have to do all the calculations and write them in the record. I am doing for only one distance d and 6 orders. Now look at this. If you look at this here, I have to measure now to note down the distance between the orders. So if I want to measure the distance between the orders, I take a scale, okay, take a scale, this is the scale here, I am keeping, and I keep at the center. This, suppose say the light is falling on 40, and here if you see, this is the first order, this is the first order. So this distance I want. So to know that distance, I am keeping exactly this spot at 40, and it is coming up to 48.6, okay, 48.6. Therefore, this is 8.6 is the distance, that is 2x. So I note down the 2x value. Before that, I have to measure the distance from the, okay, this is the grating. From grating to the screen I have to measure, that is d. So I am taking the scale here, I am keeping it here exactly on this, and I will see exactly from the center spot. I don't want this, I want only this, because this d by x will be theta. Therefore, I am just measuring this value from here to here. It is now 84 centimeters, 84.3 centimeters. So, but I can adjust exactly to some value. Maybe I am keeping this value at something like 80. So I have moved it, I have adjusted this to 80. So the distance is 80. And this distance, whatever, because I have changed the distance, this also will change around. So I have to again measure the value. So I am keeping this is the center spot, which we are showing the brightest one, and I am keeping this here at 30. If this is 30, it is falling here nearly at okay, if you see it, it is 30.2. So 38.2. So this is 8.2 is the distance between corresponding maxima for first order. Hence, I am writing here the values. First order, this is I am getting 8.2 centimeters and x is 4.1 centimeter. You can half of it because this is 2x, and this distance I have adjusted to 80. For all these orders, I keep 80 only. I am not changing and moving the distance. I am keeping all of them 80. What I have to measure? Only I have to measure the distance between corresponding values. So I have already written the first order value n equal to 1, and captain you already know it. Now I will see this one. So I am now measuring from the second order to second order. So if you see this, I am keeping adjusting at 40. This is 0th order, first order, first order. We have measured this distance between the corresponding orders. This is the first order, this is the second order, this is the second order. Now this is 42. If you see, okay, here, okay, this 56.1, but roughly I can take it as 56. This is 56, 56.5. So therefore it is 16.5. That is 2x. But the distance is same, that is d. So I will note down this value as 15.5. 15.5. So again we will just check it, how much it is. So I am keeping here it, this is, I am checking again, this is second order, I kept this as 40, okay, 40, this is 56, so 16.5. Yeah. So I have to keep this as 16.5. I am keeping it as 16.5. You do calculations, all the calculations, and I also take the next values, that is third order and fourth order also. If I just keep it here for the third order, this is the third order, 0th order, first order completed, second order completed, this is the third order. Third order I am starting from 30. Okay. Now this is first order, second order, third order. It is 55. Okay. So it is exactly 30 and 55 means 25. So third order is 35. Similarly, I will take fourth order also. This is the fourth order. First order, second order, third order, fourth order. So fourth order I keep it at a round figure, maybe around 20 here. This is the fourth order. And this is now 0th order, first order, second order, third order, fourth order. Fourth order is at 54. So is 34 this is. So third order we got 25. So write 25. This is 34. Write 34. Okay. So maybe points will be there. I am just excluding those values. Similarly, 5 and 6 orders also I will take. So the fifth and sixth orders, if I want to measure it, if I keep it here, okay, this is 0th order, first order, second, third, fourth, fifth. So fifth order I am keeping roughly at 20, fifth order, fourth, third, second, first, 0, first, second, third, fourth, fifth order. It is around 62.6. Then okay, from 20 to 62 point is 42 point, okay, this is 20, this is 62.5, so it is 42.5. So I will write this as 42.5, and make it half, we will get the values, and you have to do calculations and find the lambda value. Similarly, okay, I stop here, you take 5 readings, that is sufficient. Now, if you see these values, okay, orders and all that, okay. So this is 2x, you find x, This is D. So for 1D we have taken 5 orders. Similarly, you can change this order to 75 or 90. You can take different orders. Likewise, you can repeat the experiment. And we have tan theta x by d. This is x, this is d. You find tan theta value. Calculate theta value. Calculate sin theta value. Calculate lambda for each order. How to calculate lambda? Lambda is sin theta into n into n. N you know capital N as 2000 by 2.54 and small n you have to change as 1, 2, 3. First order n equal to 1, small n, second order n equal to 2, third order n equal to 3 and so on. So each time you have to calculate lambda and you should get this lambda the same value because we are using the same light source which is red in color. So therefore you just find out lambda and give the result as the average wavelength of the laser light is whatever you are getting, that average we have to give it.